Hello and welcome all to the third video of this HAPRA and VHDL Crash-Course playlist. This video is a really important part of our progress. So in case you didn't understand a section from the video, kindly repeat it or search for online sources to further better your understanding and knowledge of the VHDL and HAPRA module. In today's video, we will discuss 3 points of information, starting with an explanation of a VHDL Testbench and its format, and then giving you the means and knowledge to use your VHDL program and Gtkwave to simulate and generate a wave function, which we will then analyze. What is a VHDL Testbench and what is it used for, you may ask? Well, the VHDL Testbench is an important part of the VHDL program to check the functionality of the integrated circuit / program using the Gtkwave simulation software by producing a wave function and then giving us the means to analyze it. In order to achieve this, you must specify values or stimuli inside of your Testbench. Basically, you will give values, various and different values for the input signals you have in order to get a correct simulation for your design entity. Basically, the VHDL Testbench offers stimuli design under test DUT or unit under test UUT to check the output result. The Testbench consists of multiple objects, starting with an entity without any input or output ports. This is the entity declaration part, and in it we have no input or output ports. We can also have components in our Testbench. A clock, which we will explain later, and the different stimuli inputs, the inputs you give your signals to simulate the behavior of your program. We also have something called a port map, and we also have signals. The main objectives of a Testbench is to instantiate the design under test, DUT. DUT stands for design under test, and in our case, it refers to the andgate.vhdl that we discussed in the previous video. Another objective of the Testbench is to generate waveforms for the DUT and to check the functional correctness of the VHDL model, to generate reference outputs and compare them with the outputs of DUT, and all in all, provide a pass or fail indication for the program. As we have discussed in the previous slide, the entity declaration part in a Testbench has no input and output port names. It's because a Testbench is a closed system. All inputs to the design under test are driven by the Testbench. All outputs from the design under test can be observed by the Testbench itself. Hence, this is why the Testbench has no inputs or outputs. We will now look at the Testbench format that should be followed. Basically, similar to a normal VHDL program, we have the library IEEE, by which we can use any functions or variables in this library. We have our entity declaration part without any inputs or outputs. We have the entity name is entity and entity name. And in this part, we have our architecture declaration. Basically, the architecture has an architecture name of our entity name that refers to the entity declaration and has a behavior. And in this part, before the begin statement, you can either instantiate components. In our case, the component that needs to be instantiated is the DUT, the design under test, which is the AND gate. The AND gate we discussed in the previous video, as well as a port for this component. And this port inside of the component should be the exact same port with the exact same sequence of our component name. We then end this component, and we can define also signals that will be used in the test. We define signal sig1, signal 1, signal 2, signal 3 with a type. You can notice that the signals don't have any modes, don't have any in or out. So basically, you only need to specify the type, if whether it's a STD logic or an STD logic vector, or whatever the signal needs to be. Finally, after the begin keyword, we begin our test code. We should create an instance of the component name. Basically, we specify a port map that has a name and refers to our component. The component name in our case is the same as this one right here. Inside of the port map, the port name of our component takes the values of the signals of the test bench. For example, port name takes the value of sig1, sig1, and port name 2 takes the value of signal 2. After our port map, we give the stimuli for the test DUT, design under test, inside of a process. We begin the process and give the value of sig1 x. The x or y can be either 0 or 1 or even a STD logic vector, whatever you specify the type of the signal to be. So basically, let me just erase what we have right now so it becomes more clear, change the color. So basically, we give the value of x to signal 1 and the value of y to signal 2. When we do that, what basically happens behind the screen is that x is given to port name and y is given to sig2, and then sig2 refers the value to port name. We then wait for 10 nanoseconds, and this is basically the time that the result of our simulation will appear for this stimuli, and then we can specify even more signals and give them different values. We then wait, and we finally end the process, and we end finally the architecture declaration using the architecture name shown above. This is the test bench for our AND gate. As discussed, there is an empty entity declaration without any input or output ports. We have our library to call any functions or variables inside of the library IEEE. After the entity declaration, we have the architecture declaration, which flows until the end of the program. So basically, we specified a component inside of the architecture declaration before the begin keyword. And this component refers to the AND gate -VHDL in the previous slide 14, or in the previous videos. Note that the same port names must be used as we discussed in the Testbench format in the previous slide. We can also define signals. In here, we define the signal A, signal B, signal C, and gave it a type without any mode. A mode is once again either in, out, or buffer. Signals are also defined in the architecture before the begin keyword. After we instantiate and define our components and signals, we move on to the architecture body. And we have our port map, which has the name of and_G and calls the component we defined in the architecture before the begin keyword. Let me just erase this. And inside of the port map is the part of the module installation in which you specify the local signals to which the inputs and outputs of the module are to be connected, like we discussed in the previous slide. The stimulus inputs are given inside of a process, and the process is key in behavior-related VHDL model. A process is the only means by which the component's executable functionality is defined. As you can see here, we give the value of the signal A, the value of 0, signal B, the value also of 0, and in the port map, this is specified, and A is given to the first port name of the AND gate, B is given to the second port name of the AND gate, and we have the signal C, which is given or takes the value of the output of our port map. Here you can give, in this gray area, you can give more stimuli to our signals A and B. We finally wait and end the process, and finally end the architecture declaration. Basically, what I would like you to do now is to pause the video, try to fill in the blanks of the gray area, here, here, and here. Feel free to use the Testbench format in the previous slide, and it shouldn't take more than 10 minutes of your time. Hopefully you have paused the video and tried to write the Testbench on your own. If you have a similar answer to what is shown in front of you, then kudos to you. If not, we are here to learn, and this is the answer. So once again, I would like to just explain the port map now in more depth. A port map signals, the port map signals in an a port map maps signals in an architecture to ports on an instance within that architecture. Port maps can also appear in blocks or in a configuration, like shown in the component. Within an instance, the port names are ports on the component. So input 1 are port names in our component. Input 1, input 2, and result. The expressions are signals visible in the architecture containing the instance. So A, B, and C are our signals. Within a configuration, the port names are ports on the entity. The expressions are ports on the component. Hopefully you got that idea. So as you can see, we have our component andgate, which has the same port names and port of our previous video. We have declared three new signals, A, B, and C. We gave the values of A and B, B and C to the input 1, input 2, and result. And in the stimulus, we gave multiple values to A and B, and then waited for 10 nanoseconds to show the result of giving A and B the values of 0, 0 for 10 nanoseconds. We gave them A and B different values, then different values. We waited for 10 nanoseconds. We finally waited one last time, and we ended the process, and we ended the architecture declaration. On this slide, you can see the complete AND gate test bench. You can see how the stimulus inputs are defined and initialized within the process. In between each stimuli, there's a wait for 10 nanosecond statement, and that means that the simulation software should show the output of the stimulus for 10 nanoseconds each. Once again, make sure to give the stimulus inputs to the signals and not the component port names. The job of the port map is to give the inputs and outputs of the signals to the component port names. Once again, make sure to give these values to the signals, as in the port map, these signals will give the values to our component port names, and the component is then called, the output is then stored in C. We will now talk about the simulation software Gtkwave. Gtkwave is an analysis tool used to perform debugging on Verilog or VHDL simulation models, with the exception of interactive VCD viewing. It is not intended to be run interactively with simulation, but instead relies on a post-mortem approach through the use of dump files, a VCD dump. In other words, in other simple words, it simulates the behavior of your written VHDL and its test bench. It simulates the behavior of a VHDL written code, shows all inputs, outputs, signals of a module. And in the slide, you can see a user guide link, which I will also make sure to put in the description of the video. You can go into more depth with VHDL using this link. To open Gtkwave and generate a waveform, there are a total of 5 commands that you should run in order to compile, analyze, build, produce a VCD dump, and finally to start Gtkwave and simulate your program. I am not going to go in depth regarding these commands because you are going to be responsible for doing so and doing the research behind each one of these commands in your Übungen. What I can tell you is when you write the command GHDL-S followed by the name of your file, point VHDL, it runs a syntax check. -A does an analyze, -E builds a VCD, -R performs a VCD dump, and finally the command Gtkwave or Gtkwave starts Gtkwave. Once again, it will be discussed in the exercise sheets in the HAPRA module. I will now show you how the simulation of the AND gate should look like and how the person can run any VHDL program on Gtkwave to produce a waveform or wave function, and then we will analyze it. Okay, so basically we have this folder which has both andgate and andgate Testbench source code. We can edit them with Notepad++. As you can see, this is the andgate code discussed in the videos, and also the andgate Testbench, which we discussed in this video. What we need to do right now is basically open any terminal, doesn't matter. You can do this in CMD, any Linux terminal, or even the OS terminal. We need to run the command GHDL-A and then give the name of our file, which is the andgate .vhdl. If nothing appears, then the analysis is done correctly. And we also forgot to do the syntax check. Andgate point VHDL. We will also need to run the similar commands for the andgate testbench. I did that using a script I wrote, but basically you need to run the same command shown on the slide, which I showed you, that shows all the commands. The script only does that for me, and when I press on enter, Gtkwave will open. Once it does, you will be greeted to a similar page. When you press on andgate TB, 3 signals will appear, our signals that we used in the test bench, A, B, and C. I double click on A, B, and C. As you see, the wave function appeared. We can now analyze it a bit more in depth. So basically, A has the value of 0 between the times 0 and 10 nanoseconds. Wait, I'll change the color so it's more clear. Basically, we have the value of A takes 0, B is 0, and the output C takes the value of 0, since we are implementing an AND gate. When the value is 0, then the line will be in the quadrant below. When the value is 1, then it will move up a bit. As you see here, A still has the value of 0 from the time of 10 nanoseconds to 20 nanoseconds, but B took the value of a 1, and so it moved up to the upper quadrant of its field. Once again, the output remains 0. The output is C in our case, and it remains 0. Once we move the cursor to the right, we have A is 1, B is 0, and our output is still 0, since the AND gate requires 2 highs for an output of a high. This is between the time of 20 nanoseconds to 30 nanoseconds. And finally, when you move the cursor further down the right, as you see here, A took the value of 1 starting with the time 20 nanoseconds and continued to stay as a high. B took the value of a 1 after the time of 30 nanoseconds. And since the 2 input signals at the time of 30 nanoseconds are both high until 40 nanoseconds, then our output C will also be high. There are multiple things you can also do in Gtkwave. I'm not going to go in more depth regarding these. You can change, for example, the format of the colors. I can give it a yellow or a green or whatever. There are also some data formats which you can give them in decimal, hexadecimal. You can check out those on your own using the link of the guide for Gtkwave I will place on the description. Basically, this wraps up our video for today. I hope you have benefited from this lecture. In the next one, we will discuss the difference between signals and variable. We will discuss the operational levels of VHDL in comparison to other programming languages, and go in more depth regarding the VHDL and the HAPRA module. Thank you once again for your attention, and I will see you next time.